That's up and down, and this is the point next. Down is next. Gentlemen, ladies, good morning. Though I know that the clock has turned 10. My name is Per Arnold Dyrkorn. I'm a Norwegian guy. So I've been in Poland working some years back. First, thank you to Pronovum for allowing me to be here today and to present some ideas and technologies to you. My focus is the distribution network, not the boilers, but the distribution network, the pipes that produce and distribute hot water and return water out through the communities. This and my message is actually double. I will go through some of the technologies, though not in very much depth. You are welcome to see the video outside and also to discuss details. But my message is also that by using this technology, there are huge cost savings for the district heating companies, allowing them to, instead of, which is the situation today mostly, that there is a maintenance budget for the district heating pipes, and they tend to take the oldest one and replace them, or they take and replace lines which they have problems with. My message is that by using this technology, you can replace some segments and leave the rest to be for another 10 or 20 years. I will show you how. This technology has a background which is rather special, because as happened, the Poles and the Norwegians have at least one common ground, and that is that we were raped and taken by the Nazis in 1939 and 40. And the German battle cruiser Blücher was sunk in the Oslo Fjord in the spring of 1940. In the 1980s, it started to leak oil from the tanks of Blücher. And the Norwegian government asked a technology firm to try to estimate how much oil was in the tanks, to be aware if there were big leaks to come. No, they didn't find a lot of oil there, but the technology they developed had a side effect. They saw the remaining wall thickness of the tanks. We took this technology into the pipe distribution networks, focusing first on drinking water. That's why also some of the traits of this technology is focused on drinking water. With the probe we are using is naturally buoyant in water. But of course, later we have taken it into district heating. So, yeah, that's very briefly. So we assess condition of metallic pipes. And as of now, our abilities limit us to the diameter range between 300 millimeters and 800 millimeters. We aim to be able to cover up to 1.5 meters within the not too distant future. And we then, based on this technology, we are able to assess metal loss, remaining wall thickness, and by use of statistical methods, we are able to estimate remaining lifetime of the pipe infrastructure. We see manufacturing defects, leakages, problems of joints, pitting corrosions, sediments, and graphitization of pipes. We have been in the market for a period of time and inspected close to 180 kilometers of pipes. So we have some background for some of the statistics I'm going to show you, also on the financial side. As you may see, Russia is a big part of this. Because we have been doing condition assessment of district heating pipes for MOEC for the last 4 or 5 years. allowing them to replace selected segments rather than the whole pipelines. So we have a cooperating partner in Moscow. We have labs and operation crews there, engineers. It says something about the money invested. It's too much, but this is, as you all know, technology development is costly. I must say that's always market. So it's not only having the technology, you need to get it into the market. And we have been in, as you saw, several countries. Some words, very briefly. I will not go into too many details around the physics, as my honored professor friend here also did. And it reminded me actually of when I was studying plasma physics. Then some of the strange science things kind of flew back to me, though I was not able to follow your Polish, I'm sorry, sad to say. So the inspection tool that we have works in water-filled pipes. So, and there is a need for shutdown of operations. We propel the tube out and we tow it back in a constant speed while shooting signals. We cut into the pipe using hatchbox. It's a tethered solution, meaning there is a cable, because the data we assemble is very, very huge. We are talking 100 to 300 megabytes of data per meter inspected. And we can go 750 meters in each direction from the entry point. We are able to do several kilometers a day if the pipe is very well prepared, so we can go in and do the inspection. So the inspection is fairly fast. Pipe wall thickness. Normally we have inspected pipe walls, pipes with fairly thin walls, but we were challenged by Thames Water, very old pipes that has walls up to 3 centimeters, maybe even bigger. We have solved this, so we are able to handle pipe walls up to 40 millimeters, maybe more. What we shoot signals, we shoot it through the circumference so that it's a 360-degree inspection tool. And of course, the ability to locate external and internal corrosion gives us the remaining wall thickness. So with let's say with then the resolution, how small defects can we see? This is an ongoing development. In the drinking water sector, we know how the rust develops, and there were never a request to find very, very small holes. I should say that this technology was taken by another company and used in oil and gas. And they are looking for, as you know, very, very small holes. So the technology allows for this. But we have not developed it to go down to, let's say, a square millimeter or very, very small holes. So but as of now, for a 600 millimeter pipe with depth defects of a couple of 3 millimeters, we see these 5.5 centimeter areas very clearly, no problems. 3.3, we see them very well. When we are closing down to a centimeter or a square millimeter area, then we are having some problems. But for all practical purposes, for district heating and for drinking water, this is good enough. We have two-layer inspection capabilities, as I mentioned when I started, meaning we are able to inspect concrete line pipes, and this is of course a big challenge. And actually this is also one of the reasons why we ended up in Moscow, because the cooperating partners line steel pipes. But after the lining of concrete lining, the Russian regulation says that you have to test the pipe with a pressure up to 25-30 bars. And then of course if you had external corrosion, which they didn't know of, it blew up. So they wanted a technology that could tell them where is the external corrosion, what do we need to replace before we spin the concrete lining internally. Bends, we are able to handle bends, but not 90 degrees bends. So we can do some deviation from a straight line, but this also depends on the diameter of the pipe, which you will all realize. We know at each and every second where the scanner is in the pipe. And one for the drinking water, obviously not so important for the district heating, but we are not supposed to compromise water quality. And that's also one of the reasons why it was developed, this technology, together with Oslo VAV, the drinking water company. So it's not, the inspection tool is naturally buoyant in water, and we have calibration arms that keeps it in the middle of the pipe, but very lightly, so not to destroy rust nodules, because this is a problem with trawlers. They tend to crush the rust nodules internally in the pipe. Max temperature, without going into details, 50 degrees. The problem here is mostly that people are not allowed to work with these very high temperatures. This is obviously something that we are looking into, whether we can have a kind of a hot tapping system. Pressure in the pipes, inspection not performed when the flow is switched off, which normally then reduces pressure. So this is it. And this is the internal pipe inspection tool. It's a lightweight thing, 30 kilos, though you need some equipment to obviously to lower it into the pipe. All of this can be seen very easily in the video outside. When we process this data, we come up with plots that shows wall thickness, type of defects in the pipe internally, also external rust, internal and external defects. We see how deep they are, whether it's external or internal. This is a plot from the Lehigh Road inspection we did in 2017 of a very, very thick pipe. This is drinking water. This is a picture of how a report might look like, showing that this pipeline with the red segments needs replacing. Some you need to keep a watch on, and some is fine. This is actually, the normal situation is that there are only a few segments that needs replacing. In Iceland last year, we did inspection for Veitur, 6-7 kilometers, and it was 9 pipelines. And when we presented the first report, the first line, the director said, "Jesus, you just saved me for 600,000 euros for this line alone," because they had already decided to replace it. But the thing is that our inspection showed that they could replace only 6 segments at the end of the pipe, and then it would be good. And then the engineer started saying, "Yeah, that's right, we have only had problems in that part of the pipe." So to the economics. And I think this is the most important thing, because we develop technology, and as technologists, physicists, we love technology. We love to do something. We know the bits and the bytes, and we love to see it work. But in the very end, it's all about economy. So why are we doing this? And the logic is that if you look, this is a sample from our more than 100 kilometers inspections in Moscow. And these 20 kilometers, these pipes were initially planned for replacement. Our inspection gave recommendations on how to handle this. This saved MOEC 50 million euros. So we are talking fairly big amounts of money, which you all know is a costly affair, these pipelines. The same with Oslo, where our recommendations saved them more than 60% of initially planned cost. So this is my message. Hopefully I didn't overspend my time. And this is the nice place where I come from. I love to call it a nice place. Actually, it's not only Norwegians up there now. If you go through the main street, it's mostly Chinese. So we had a discussion yesterday over the globalization and what's going on. So if you want to visit Chinese, come to Tromsø. Thank you.
Thank you. Bye.